So I'll show you guys a play blast of what we're after here. This is the debris that we just made, plus the debris that I'm about to show you where it's falling down vertically from the cloud. And so the debris that I'll show you how to make here is going to be right around here, these guys. So notice how they just sort of fall down and they spawn from the cloud itself. That'll add a subtle but yet noticeable body to the debris overall. And you can add more than this if you want it to be less subtle. But I want to show you how you can do this. And probably the easiest way is just to draw over this. So overall, this is fairly straightforward. We'll take our density, we'll make a volume that's based off of the bounding box of the density. And all we'll need to do is take this box, this bounding box, turn it into its own volume and fade the density values from the top to nothing towards the bottom. What that will do is it'll give us something to multiply against this density plume, and it'll cut off areas down here so that when we go to spawn these particles, they only happen up towards the top. So that's the first step, is isolating the area where we want to spawn the points into. Once we have those points, the next step is to take those points into a particle simulation. With the velocity, we'll simply take the velocity of our simulation and add that in. There is a advect particles by volume node that we can use for that. And so that'll take the particles, spit them outwards away from the cloud a little bit. In addition, if we want those particles to go out away from the plume, we can also source in velocity by creating an object out here for the points to look at. So, imagine some polygons that's kind of wrapped around like a donut for this entire explosion right here. If we have the particles look that way, then we can also have another control for moving them away from the cloud if we want. Once we have these particles falling downwards, what I'd also like to do is have them reduce in size from their p-scale. This will create an illusion, this is kind of a hack, but it'll allow us to not go through the whole process of an RBD simulation. Because this is a more subtle effect, the viewer won't even notice if these rocks are going to slightly fade into a p-scale of 0 towards the bottom. And so that allows us to keep this as a particle simulation rather than an RBD simulation, which is much more simple and straightforward. And so as the particles fall down, p-scale reduces. The way that we can do that is having another box like this with another volume fading from top to bottom. And we can then use the values of that volume to multiply against p-scale. So that is the gist of what I'm about to show you. Let's jump into Houdini and I'll show you what the setup looks like. All right, so starting with the new network called Falling Debris Build, we first start off by bringing in the density from our sparse simulation. Let's go ahead and hide other objects for right now so that we can see this. And as soon as we bring that in, again, we want to isolate the top here. That's going to be where we place those particles. You could also import the vorticals from your DOP simulation. However, I like this technique better because it doesn't rely on you re-simulating anything if you want to grab areas for points to be. Anyway, we first of all isolate density right there. We take the bounds. We then turn that into a volume. I have a very coarse volume right here. We don't need a lot of resolution for this. I then use the volume adjust fog to create a fall off that looks like this. And this is a brand new node to Houdini 19. So if you've never seen this before, then check out the node Bible link that's popping up on the screen. That's a very great node for, again, all kinds of different operations, especially when it comes to fading based off of the bounding box. So that's what we have right here. Pattern type bounding box, enable with a remap ramp. And I've specified that about halfway through, we are cutting off all density. We then use a VDB combine to cut into that density cloud. I've said that we want to take our higher res mesh to match the lower res. That way, again, our resolution is small. This goes quickly. The operation is set to multiply. And then we scatter some points. These points are going to be, again, what we use for spawning all the different points at every single frame. So we go ahead and do that. This gets cached out with the test particles. It's brought in right here so that now we end up with something like this. It's very chaotic looking, but not too bad because this, again, will be where things spawn from. And then once we get to this point, we're thinking about velocity. We're thinking about where we want to source that velocity from. As I mentioned before, you could take a sphere, cut it off so that we basically have some scattered points surrounding the simulation. So, this would be where the plume is. All these points are kind of in this donut shape along here. And then what I'm saying here with this set velocity is what we've seen before. We looked at the nearest points off of this stream right here. We sample its position, we take the difference, and then that becomes the normalized velocity. Again, I've already mentioned this technique before, so if you're not familiar with that, then go back and look at what we did for sourcing velocity in our main pyro simulation earlier. So anyway, that'll give us some velocity vectors to work with when trying to get this away from the plume. We then randomize mass, p-scale a little bit, and going into the PopNet, there's a couple of things that I've sourced in. For one, we have the original plume, I've isolated velocity, and then I've downsized that velocity resolution so that it's way less voxels. If we keep the velocity at 24 million voxels, that's way too much. So we can do a voxel size of 0.2, maybe even more coarse at about 0.3. That gets cached out and read in right here to the second inputs. And then after that, I simply bring in the terrain so that we can collide our particles with that terrain and have the particles die if they hit. So now, going inside the PopNet, we source in our particles based off of the points that we've specified earlier. We use the first context geometry. The birth is keyframed to last only for maybe a second or two once the pyro simulation starts. So I kind of ramp up right here to a value of about 1,500 particles a second, and then that gradually ramps downwards as the simulation progresses. Now, we don't have our particles dying at all. That will be taken care of with the collision impact. So down here at the pop solver, I say that if we hit anything, go ahead and die. And then with the pop advect volumes, we're bringing in that velocity. We're not treating this as wind because that'll match the velocity of the simulation. I want the velocity to look a bit different than what's happening in the plumes. So that's why I've turned off treat as wind. And I'm also unchecking ignore mass to add a bit more randomization to the whole thing. In practice, if I turn up this velocity scale, it has the effect of sort of spitting particles out from left to right, as well as going up top and spitting it out that direction. So it's kind of finicky, but I think around 1.3 is pretty good for this situation. The pop drag is fairly aggressive. You want to be sure that these particles are falling at about the same rate as what we see happening with our main debris. And so I found a value of 0.15 to be pretty good. And then the velocity that's pointing outwards with these vectors right here can be controlled by how we import velocity right here. So if I want this to fan more outwards, I can just bring that up. And again, that'll spit the particles away from the main plume. So that all comes together. One last thing actually that I did on this is I took a gravity and I set this to a low value because I don't want these particles falling too quickly. So negative 0.5 seemed to do the trick, and that all gets cashed out right here. Once those particles are cashed out, we end up with something right around here. So some of these guys get thrown up with the plume, some of them are raining down. That's pretty good. We then go through the whole process of selecting a variant and copying rocks onto the variants. So that's what you've already seen before when we did the debris, right? So we just take our rocks, maybe about 5 of them or so, clean up any attributes, and set them as packed objects with this attribute called variant select. Once we do that, I convert that over to an integer, And that gets used on the copy to points here to select the rock that matches with the points. So that's basically what we see happening right here. And that gives us our debris that looks like this. Now, one last thing that will control the p-scale of these rocks is that volume fall off. So I mentioned before that we have a huge box. This covers our entire simulation. So if I say show all objects, this will just give you an idea. It's a huge box, right? I turn that into a volume. I then use the volume adjust fog to change it so that it's just hovering above the surface like that. And then once we have this, we can then simply take a sample of that volume using the volume sample function and multiply that against p-scale. That will cause the rocks to shrink down into nothing as it approaches the ground. And that's it. That becomes the debris that falls from the cloud. So now I think it makes sense for us to move on to lighting, rendering, and shading. You could add more particle sims if you'd like. Perhaps you want additional dust passes. Perhaps you want additional debris that's particle based. Really, you can do all sorts of different things for spawning particles in different areas. All you need to do is isolate the area, define the velocity, and have it fade to a value of 0 as it gets closer towards the ground. Do keep in mind, though, that that illusion will break if the debris ends up being too big. So this is great for small details, not mid-sized or large details. Anyway, like I said, in the next video, let's move on to rendering.